Hey everybody, this is Larry. This is me on January 15, at least 15 here in New York. I don't know the timings and stuff like that, but I am going to try to do a problem that I haven't done before. Get my money's worth on the Leetcode Premium. So hit the like button, hit the subscribe button, join me in Discord, especially if you like these extra problem video things, and just give me a little bit of encouragement. But yeah, today's problem is 2792 count nodes that are great enough. It's a premium problem, it's a hard problem. We'll see how hard it actually is. It seems like that not many solve, so it may be actually very tricky. We'll see how that goes. And I should have limited a little bit because I did wanted to go to sleep a little bit early. I did go running earlier today. If you watch my other video, you might know that it's -2 Celsius here in New York, or like 25, 20, something like this, Fahrenheit. So I am just like drained, and then I ate too much afterwards. Got a Chipotle, and they really hooked me up today. But I'm just getting food coma at some point. All right, let's take a look at today's problem. 2790 I can't even say. 2792, count nodes that are great enough. You're given a root to a binary tree and an integer k. A node of this tree is called great enough if the following holds. Its subtree has at least k nodes. Its value is greater than the value of at least k nodes in its subtree. Return the number of nodes in this tree that are great enough. Okay. So the first thing I wanted to do is kind of make sure that I'm not doing anything silly. And the way that I don't do that is look at the constraints. So node, or not this part, that's just the value. So there are 10 to the 4 nodes, 10,000 nodes. It just kind of makes sure that I cannot do n square, right? If I have an n square, I'll go, or if n is small enough, then why am I wasting my time? Let's just get it done. The second part is it's that k is less than 10. So this gives us an idea of maybe not necessarily brute force, but something a little bit sloppy would be okay, right? Something on the order of k times n would be like 10 to the 5th, and that would be okay. It also means that you could store up to 10 nodes like on each node. And then the next idea then is that we have to look at the greater value of so the first thing that may come into your mind may be like some sort of sorting thing and kind of pass above the tree. But then this is where we have one optimization, one greedy thing. Sorry, I'm like, I don't know. My table's a little bit messy. I was trying to clean something for some reason. But yeah, in a very naive implementation, you may just like return all the nodes in a sorted order, maybe just. Doesn't even have to, I guess you could do a for loop. But now what you can do is you just keep returning k nodes, right? And basically in like a merge sort kind of way, then now you can keep track of the smaller nodes. And here you just have to be bigger than k nodes. And so in a greedy kind of way that let us shortcut this is just keep track of the k smallest nodes up to a tree, and then use kind of merge sort thing to go up, right? And you can prove that, because on every merge, only 10 nodes, if you kind of do it correctly, only 10 nodes gets propagated up, or k nodes really, but where k is 10, and you could use merge sort, right? So it's actually an O of k merge, O of 2k merge, if you want to say that. But yeah, so only be O of k merge, so then this is going to be k times n is the complexity. And given that complexity, that should be really easy to do, or not easy to do, but easy to prove, right? Like, I know I'm probably going a little bit fast on this video, but I feel like this problem isn't super hard, even though it is quote-unquote hard. Wish I got this on contest. I would have gotten it very quickly, which I don't normally do. But yeah, you have you just kind of return 10 elements from the left, 10 elements from the right, include the current element, and then pop, and then you go, right? So yeah, that's pretty much it. Yeah. And then return the number of nodes that are great enough. So yeah, so I'm going to use a global just because I'm a little bit lazy. But you just return a tuple as well if you really prefer. I think maybe that's fine. I don't know. But yeah, here I'm going to just write traverse, right? traverse node. Okay, so node is none, then we return empty array maybe. So then this returns up to k smallest nodes up, right? So then here the return value is maybe I'll just do something like left is equal to traverse node dot left, right is equal to traverse node dot right, and then here yeah, and then now this is just regular merge sort stuff, right? So maybe I'll even use a helper function. So yeah, so R is for results, I don't know, right? Merge left, right, and then here, you also want to merge the node dot value, which is also a little bit, I guess you could do a binary search and then insert. There's only 10 elements, right? So it's not that bad. Okay, fine. Merge. And then maybe node dot value just for, you know, whatever, and then we can return R. But maybe we also need to do a check, which is yeah, for X in R, if node dot value is greater than X, then I don't know, just add some count, right? And then if count is greater than or you go to k, then we can you know, we can increment total. Though of course, I don't know, like I said, you can actually just like return this as part of tuple or something like this, but I don't know if that's that much cleaner, to be honest. I don't know, maybe it is. But yeah, and then we have a merge, we have a left, we have a right, we have a current node maybe. I mean, that's just a little bit awkward, but that's fine. But yeah, basically merge and keep the smallest k elements. I'm gonna be a little bit lazy, so we have to do right, and then maybe you have something like L index is equal to 0, R index is equal to 0, and while left index is less than length of left, and R index. And this is just regular merge sort stuff, right? And then if oops is less than right of L index, then R dot append left of L index, and this is wrong. Very easy to make mistakes though, but yeah, right? Pretty straightforward stuff. And things that, to be frank, I've done enough times, but also probably made enough mistakes. But yeah, now we have R here, right? And now we just have to insert current. I actually don't know how to do that, but I'm just gonna be lazy. So you have R dot bisect dot bisect left R current. So you have this insertion index is what they say, right? So then now I think I never do this because it doesn't make sense usually, but array insert at index. I think it's like insert with like a thing, but I don't use it because it, like I said, it doesn't usually make sense. So you want to insert at index the current, right? And then here now we want to trim up to the last k element. So then we just kind of do up to the k, right? And that's pretty much it. Yeah. Oh, did I not call anything? So yeah, we traverse the root node, and then we can return total. Unless I missed something, which is very possible. Oh, wow. In all my stuff, I forgot to increment stuff. And also, once again, I made this typo. I guess I needed to catch that anyways. And I don't know why I'm so bad at this. Just used to using C++ for loops even years later, and I still make these kind of mistakes. But yeah, it looks okay. But the real test would be time limit exceeded, right? I mean, this was going to work anyway. Yeah, I mean, you know, even if you, I think the The only thing that's difference between this and a version that's time limited is actually just this thing, right? Because now this bounds the number of elements to k, so then now merge is bound by also k. I guess the way that this is log k, but this is also k, so that's why this is going to be O of k. If you don't have k, if you don't have this one symbol thing, then it actually, this grows quadratically even, right? I mean, just regular merge sorts, degeneracy stuff. So yeah. Otherwise, everything else is just, like I said, just kind of keep merging up. And even in the worst case, like I said, you only have all the elements on one side or something. You have like a linked list, it'll still only be 10 or k times n. So yeah, so that's the complexity, that's the space, and that's all I have for this one. Let me know what you think. Here's the merge step one more time. Here's the traverse step one more time. And here's me going to take a nap one more time. So yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.